I think it's an interesting fact to let you guys know that back in high school, I actually failed the electromagnetism course in my physics class. And I remember taking a test and it was like, there was a circuit problem. And I just stared at it for like the entire test and I was baffled. And I guess that just goes to show that you can do whatever you want if you immerse yourself in it completely and ignore all other aspects of life. So, yeah, let's see that Tesla coil. Everybody, welcome back to Swae, and in the last Tesla coil video we chose our power supply, and in this video we will determine what kind of primary coil and what kind of secondary coil we need to transform the energy provided by the power supply into bolts of beautiful lightning. Like I said in the last video, I'm modeling my Tesla coil off of this spark gap Tesla coil built by YouTuber Pyro because I want about 2 to 3 feet of lightning like him. After a little research, I stumbled upon a wonderfully helpful website called Deep Fried Neon, and I discovered how the length of the output lightning is directly related to the input power and the size of the secondary coil. Here you can see the equation and related charts that the website provided. This told me that if I wanted the same size of lightning that Pyro made, I needed a secondary coil like his. So that's exactly what I did! I got the exact same coil as Pyro. Okay, the secondary came in like a week ago, honestly. I've just been too nervous to unwrap it because there's a small gap here, and I'm gonna try and fix that right now. This is not going well. And so I couldn't fix it, and it still had a gap in it, so I got a new secondary coil, and that's the one you're seeing me unwrap right here. And so it's one continuous strand of copper wire coated by enamel, and by putting the physical dimensions of the coil into an online Tesla coil simulator, I found that the inductance value is 29.6 millihenries. Now that we have the secondary coil, we can make the other part of the secondary circuit, the top load. The top load is a smooth metal object electrically connected to the top of the secondary coil. It is usually made of aluminum because of aluminum's high conductivity and low cost. The best shape for a top load is a toroid, also known as a donut. This is because the toroidal shape allows charge to evenly build on the surface, which reduces charge loss via corona discharge. As for the size of the top load we should use, most coilers make a toroid with a minor diameter equivalent to the diameter of the secondary coil they're using, and a major diameter 3 to 5 times the length of the minor diameter of the toroid. Kinda confusing, I know, but you just gotta build it. The top load acts as one plate of the secondary circuit's capacitor, and the other plate is, most notably, the Earth's surface. And when I put this top load's physical dimensions into the Tesla coil simulator site, along with the secondary coil dimensions, I get the secondary circuit resonant frequency. This is the frequency that we need the primary circuit to resonate at as well. In order to get the primary circuit to resonate at this frequency, we need to design a primary coil with an inductance that combines with the primary capacitor's capacitance to give the same resonant frequency as the secondary. And we can rearrange this resonant frequency equation to get the primary inductance that we need for our primary coil. So we plug in the 3 values that we just found, and the primary inductance that I need for resonance is around 12 microhenries. With that value in mind, we can now start designing. The construction of primary coils is not thoroughly documented on YouTube, so I had several questions when I started my research. I wondered, what kind of conductor do I use? How does inductance change with physical dimensions of a coil? On that note, how do I wind the primary coil? What is a coil, honestly? And then, how do I connect the primary to a 3D circuit? And so I went back to old reliable Pyro, and I saw he was using this kind of copper conductor. It's 3/8 inch copper tubing, but it's expensive. So I was like, I'll try to avoid it if I can. So I looked at some other sources. Another person used this kind of wire. It's like solid wire, thick gauge. Same kind of thing for this person, but it kind of looked janky. I wanted my coil to be clean. And then I found out about the skin effect, and that's why Styropyro ended up using 3/8 inch copper tubing. And so I ended up using 3/8 inch like Styropyro. Big surprise. The easiest primary coil to make is the spiral coil because its inductance only depends on 4 variables: the inner radius, the outer radius, the wire width, and the wire spacing. You should note that if you use Java TC, it calculates its values based on the center of your wires. We know our wire width is 3/8 of an inch, and from Styropyro's design, it looked like he used 1/2 inch wire spacing, and it worked for him, so I'm using that value for my coil as well. The inner radius of your coil is the sum of the secondary coil radius, the distance to your first winding, and 1/2 the wire width. For our last variable, the outer radius, we can find that value by adding the product of the number of turns and the sum of the wire width and spacing to the inner radius. Now we have all the values we need. Okay, I guess there is one more very important variable I just mentioned, which is the number of turns, but you just start at 3 turns and input larger and larger values into Java TC. Once you match your resonant frequencies, you're done. Congratulations, you now have a primary coil that will resonate with your secondary coil. But there is one tiny little electromagnetic caveat that we haven't discussed yet, and that's coupling. I promise I'll explain what it is in 1 second, but for this size Tesla coil, you should have 1 inch spacing between your secondary coil and your first coil of your primary coil. That will allow for generally good coupling. In the world of Tesla coils, the coupling coefficient is the ratio representing how much of the primary coil's electromagnetic field is coupled to the secondary coil. And the coupling coefficient increases as the primary coil height increases, or the primary gets closer to the secondary coil. So with that being said, a spark gap Tesla coil should have a K value between 0.13 and 0.22, and my coupling coefficient ended up being 0.126. If your K value is too high, you may get coil-to-coil arcing, which can send your coil to the graveyard. So in summary, you should use a flat spiral coil and let Java TC design it for you before you start building. But now you gotta build it, and you're gonna need some help with that. Luckily, I know exactly who can help. My dog Oreo and my father.
You what?
So with their help, after about 700,000 hours, we came up with this. I know you're impressed. You don't have to say anything. And so I went back to this design and I was like, all right, there's something here. And that something is that this wooden frame can hold my coils at regular intervals. So I drafted up my own design. I inputted it into SketchUp, which is a 3D design software, so that I could get a better look at it, and I started building it.
It's my life, and it is generated.
Like the Atlantic, and I'm going down like the Titanic. It's blue like the Atlantic, and I'm going down like the Titanic.
Eyes blue like the Atlantic, and I'm going down like the Titanic. Eyes blue like the Atlantic, and I'm going down like the Titanic.
Blue like the Atlantic, and I'm going down like the Titanic.
Eyes blue
Like the Atlantic, and I'm going down like the Titanic.
You hurt yourself.
Like the Atlantic, and I'm going down like the tide. Like the Atlantic, and I'm going down like the tide.
Eyes blue
Like the Atlantic, and I'm going down like the Titanic. Like the Atlantic, and I'm going down like the Titanic.
Eyes blue like the Atlantic, and I'm going down like the Titanic.
Shee! Look at that, bruh. Tweezers. Zip ties. Primary coil. I know she vibing over here too. Don't pretend like you weren't watching. And in fact, she did tell me later that she was indeed vibing and watching me. And as cute as that may be, you may still be wondering, how do I wind the primary coil? Well, you make primary formers, you invest a little time, and you invest a lot of zip ties. And now we come to the final step of the primary coil construction. How do you connect your primary coil to the rest of your circuit? The inside of your primary coil should lead to one side of your capacitor bank, and the other side of your primary coil should lead to one side of your spark gap, and that spark gap is connected to the other side of your capacitor bank. Here's how I made mine.
Eyes blue like the Atlantic, and I'm going down like the Titanic. Eyes blue like the Atlantic, and I'm going down like the Titanic. Eyes blue like the Atlantic, and I'm going down like the Titanic.
Like the Atlantic, and I'm going down.
Then I cut another piece of copper tubing and some wood supports to make the strike rail. The strike rail protects the primary circuit from discharges by providing them a less resistive path to ground. If these high voltage discharges did hit the primary coil, then the capacitor bank or power supply may be destroyed, and we don't want that. Here you can see me bending the strike rail down so I can connect it to RF ground later. What's grounding? In the context of spark gap Tesla coils, grounding is when you connect the bottom of your secondary coil and your strike rail to a conductor that's been stabbed into the ground. RF grounding is essential to building a functional spark gap Tesla coil because the earth provides the secondary coil with lots of charge. Grounding also reduces the amount of electromagnetic interference emitted into the surroundings, which could get you in trouble with the FCC. So all we need to do is design a part to electrically connect the secondary coil's thin wire to the earth and mount the secondary coil in the center of the primary coil. Luckily, other people have already made great designs for this part, and it's called an end cap. This end cap was designed by the company 1 Tesla. It is fit snugly and glued into the bottom of the secondary coil and secured and grounded with 3 machine screws that align with 3 holes in the top of the circuit enclosure. The mounted coil looks like this, and the end cap is right there. Here's my design. Let me show you how I made it. I cut a piece of plywood into a circle and sanded it, then drilled 3 holes into it to place mounting screws. Now we're gonna fit this into the holes. This is what we call a fit check.
Yes, sir.
Then I drilled a hole in the bottom of the secondary coil, and I carefully pressed the end cap into place. Now I'll thread the end of the secondary coil through a hole. We got 'em! The calculations are lit. We do be making it happen though. And now I sand off the enamel from the wire, and the bare copper is now exposed and can be electrically connected to this brass screw. Let's do a dry fit test. Here goes nothing. modular. Woo! Now all we need to do is put some terminals on some wires to make a grounding system. And here I am putting a little washer on the brass screw and connecting the wires. And here it is up close. And this is where it leads to, right next to the strike rail. And I can connect these to some threaded thick copper wire. And I tried to do it during a thunderstorm and I got some help. And here it is, secured by a hose clamp. And actually at this point in the build process, I did not have the big secondary coil like I showed, and so I made this tinier coil. And I also had to redo the tuning calculations, you're right. So I put it all together and here it is, yay! We did it! Off camera, I put a copper pipe connected to the stranded wire of the grounding system into nearby soil and connected a line filter between the high voltage power supply unit and the wall socket, which protects my house from catching on fire and burning all of our possessions. Okay, here's the first test. Hello everybody, this is Tate here. It's March 16th and I'm going to do my first light of my Tesla coil. I'm going to turn on the fan for the spark gap first, and then a few seconds later there'll be hopefully a very loud crackling noise and lightning coming out of the top. And hopefully it doesn't immediately explode. So here we go. Turning on the fan. Fan's having some trouble, 1 sec. Here we go. Mini Tesla coil in 3, 2, 1. Okay, that was awesome. Yeah. Okay. Woo! Yeah, lightning! Okay, one more time. And I ran it a few more times, redesigned the spark gap, primary tap, almost took my hand off with the drill. Among Us, set it for the bigger secondary coil, ran it, but it was lame, so I gave up. Just kidding. I was like, oh, I'll widen the spark gap, and then this happened. 2, 1. I did. 3, 2, 1. Let's go!
You know how many things can go wrong doing this and you were able to get it to work?
2, 1.
Electricity, yo.
Now, hopefully you're not insane enough to have this thought, but logically in my brain I thought, I will now touch this. So I did some research and I bought a metal glove and I grounded it and... And no, I didn't let anybody else do the stupid glove thing, don't worry, but I did invite my neighbors over and they enjoyed it. Alright, Tesla coil in 3, 2, 1! Whoa! Yeah, the soda can had lightning on it. I want to give a big shout out to Styropyro, Diode Gone Wild, and Lab Coats for all that they do to inspire their viewers, and I wouldn't be able to complete this project without them. So, that is how you build a spark gap Tesla coil, and how I was able to touch lightning. Dream big, persevere, and you might shock yourself with what you can achieve.